I'm not sure whether I pronounced correctly. So Parvaneh, can you try to share a screen?
Yeah, sure.
Okay.
So can you see my screen?
Yes, very well.
And
okay.
I hope you can hear me well enough.
Yes, we can hear you very well. Okay, now we have our second speaker, Parvaneh Joharinad. She will talking about curvature of data. Okay, please.
Yeah, thank you. Hi, everyone. And I want to thank the organizers for arranging this talk, this conference. A lot of really interesting topics, although the timing is a little bit difficult for us from Europe to attend all the talks, but I'm trying to participate in as many as I can because the subjects are really interesting from the perspective of geometric and topological data analysis. So, but here today I want to speak about the concept of curvature. The topic that I'm presenting here is the result of the joint work with Professor Jürgen Jost. And I want to start from looking at which type of geometric data analysis is interesting for us. But first, I want to see what we say or what we see as geometric data analysis here. For instance, when we talk about the topological data analysis for metric spaces, the really well-known method that is used in many different areas right now, we try to look at the intersection of both, and from that, we want to infer the shape of the underlying topological space. But from topological perspective, what we have are homologic groups and Betti numbers as topological invariants of this underlying topological space. But on the other hand, when we go to geometric data analysis, we have our data set, but what we are interested in is the rule that is governing the relation between these data points. So in some sense, we want to extract the geometry, underlying geometry, that is this rule that is governing the structure. For instance, in most of the methods in dimension reduction nowadays, people are looking at to find the underlying Riemannian manifold. That means we want to find the distance function, the exact distance function in the lower dimensional embedding space. And if we try to extract this Riemannian structure, what we can consider as geometric invariance, we should look at curvature, because due to the theorem of Riemann, this sectional at the beginning, sectional curvatures are fundamental geometric invariants in Riemannian manifold. But when we talk about curvature, we might look at different types of curvature. So even in Riemannian geometry, we start with sectional curvature and then the average sectional curvature to obtain Ricci curvature, and then again we average this Ricci curvature to get a scalar curvature. But some of these concepts have already been generalized to more general spaces, like the Gaussian curvature, which is the sectional curvature of two-dimensional Riemannian manifolds, which has been generalized to the case of finite graphs. And the idea is like that if we have a finite graph with some constraints on the genus of this finite graph, we can just embed it in some two-dimensional surface, and then we just need to compute the Gaussian curvature of this surface, and that would be the Gaussian curvature, graph Gaussian curvature of that vertex. But although it is quite like sectional curvature, but at this point, it just gives us a value at each vertex or at each point in our data set. But if we go further from this one, we come to Ricci curvature. In Riemannian geometry, what we know about Ricci curvature is that we take a vector, a tangent vector, and we assign a number to that vector, and it would be our Ricci curvature. But here in data set, we don't have any vector. So we try to imitate this vector structure in our data setting, and the best way to do that is exponential map. That means that if we have our tangent vector, we can just start from the initial point of this vector and just use this tangent vector as the velocity at the beginning, and then we go in the direction that this is defined by this vector to get to another point on Riemannian manifold. So then we can say that, so if we want to imitate this vector on our data set, we need 2 points, and therefore the Ricci curvature that we want to assign to this number, it would be a pair, the quantity that we assign to pairs of points. And so there are different versions of Ricci curvature, but just to say that whenever we go one step forward, we need to consider some extra assumption on our data set. I just brought the Olivia Ricci curvature here, where we have the metric space as our data set, but on the other hand, we also should have a random walk on this vector space. And what we do here to obtain the Ricci curvature is not exactly the Ricci curvature, but it is some kind of a lower bound on Ricci curvature. And this lower bound is determined by looking at the Lipschitz constant of the function that is dependent on this vector, on this metric space and the random walk. And to make it more clear is that we define a function from metric space X to, maybe I use the annotation here. Yeah, we use a function from metric space. Oh, yeah, we use a function from our metric space X to the space of probability measures. And this function, just remember that we have the random walk. With random walk, that means that we have a family of probability measures indexed by the points on our metric space. So we define the function from X metric space to a space of probability measures, taking each point to this probability measure that we have in our random walk. And we just look at the Lipschitz constant of this function, and it tells us what would be the lower bound on Ricci curvature in this structure. But anyway, with this extra assumption of the existence of random walk, we can define a lower bound on Ricci curvature for our metric space, which is a pair dependent function. So it takes a pair of points and gives a quantity. So then from here, we come to sectional curvature. What we have in Riemannian geometry is that we pick a point, we go to the tangent space at this point. There we take 2 vectors that generate a plane on that tangent space. And then sectional curvature is a number that we actually are assigning to this plane. But again, we can do the same thing as Ricci curvature. That means that we don't have any tangent space, we don't have any vector here, but we already can use these 2 vectors to go to 2 other points on our Riemannian manifold, just going in the direction that are defined by these 2 vectors. And then we have our base point and 2 other points assigned to the end points of this vector, so it would be a 3-point. Therefore, if we are going to define a sectional curvature here, then we need to define it as a triangle base quantity. That means that takes a triple of points and gives a number to that. So what we are trying to do is doing the last part, that is generalizing the concept of sectional curvature to metric spaces. But not just exactly the sectional curvature, but the upper bound of sectional curvature have already been generalized to metric spaces, specific ones or discrete ones, quite long time ago, like by Alexandrov and Boozman for geodesic metric spaces. Geodesic metric spaces are metric spaces where you can define, you can find a path between any 2 points that realizes the distance between those 2 points. And even for the discrete case, by Gromov, that the difference between Gromov's definition and the other ones is that the 2 first ones are again triangle-based quantities or conditions, but for Gromov, we need 4 points. So we get rid of geodesics on the metric space, but on the other hand, we have to add one other point in the condition. So what is important about what is different between these ones if you go to the realm of data analysis? First of all, if you don't have the network, that is somehow you can construct the graph, put some metric structure on that. That means that you have paths between points, so it is naturally a geodesic space. In other cases, we don't have these geodesics between points. That means that we come to difficulty if we want to restrict ourselves to the conditions that were defined by Alexandrov and Boozman. On the other hand, even in networks, applying these conditions is really hard, because in the conditions that is introduced by Alexandrov, you need to find the condition on the distance from each point to the edge that is across this point. And when you think about computation, it will be something really disturbing to do so. But anyway, these conditions have been applied to real data sets, at least to networks, and it has been understood that even though most of the networks that we are dealing with, like social networks, collaboration networks, satisfy in this negativity of curvature condition, the other model networks that are generated or introduced to study this kind of real network do not satisfy in this property. So it is something that is missing here in the construction of these random networks or model networks. But what we want to do is we want to go one step forward. So we want to define a type of curvature or lower and upper bound on sectional curvature that would be somehow related to other techniques that we are using to study our data set. So we already know that when we have our data points, we can start working on this data point from topological point of view by considering balls and then looking at the intersection and just constructing these simplicial complexes. And this is the well-known technique of TDA, and seeing what is the shape of this data set. So we want to use the similar idea, but then obtain something about the geometry or the sectional curvature. So we want to focus on these metric balls around points and see what happens, what does the pattern of this intersection tells us about the curvature, other than the thing that is telling about the topology of the space. And what we see at the end is that we not only are capturing this geometric information from this intersection pattern, but we are focusing on some kind of convexity or higher order of convexity. These are the parts that I'm going to emphasize in this talk. So now we come to how we define this sectional curvature. What we do at the beginning is that we pick 3 points. So we want to define a function on 3 points. We pick 3 points and we draw 3 balls around this point. But these 3 balls have the property that if they are going to meet pairwise, they should meet on the boundary. So if we are going to have the pairwise intersection, the intersection should be on the boundary. So in geodesic spaces, this condition could be quite easy to obtain, but in metric spaces, we might not get the intersection, but at least we can expect to have such an intersection. And we just say that if we expect to have an intersection, it should be just on the boundary. So finding such a reduced function or initial bulb is not something that is difficult, because we just need to write down our condition in mathematical words. And that means that we just want the radius around bulb to add up to become the distance between centers. And this would be enough for us. And this one is just a very easy system of linear equations. And the interesting thing is that the solution that we obtain from this system of equation is exactly the Gromov products of these three distance functions. So now that we have our initial three bulbs, we start enlarging these ones, and we look at the time at the first moment that we get the intersection. So we look at the smallest or the infimum scaling factor where we have the intersection of the triple. Or if we want to write it down in mathematical words, it would be just we take the infimum over the maximum of these quantities. So this number is something that is going to be at the end our sectional curvature for this triangle. So we should just notice that we might lose some parts of the sectional concept of sectional curvature in Riemannian geometry here, because we have already changed the plane with these two endpoints. And if we look at the structure in Riemannian geometry, what we have here is, so in Riemannian geometry, what we have here is that we have our Riemannian manifold. We have this point, like we choose which one is x1, and then we just take the plane that is taking us to x2 and x3. But on the other hand, here we don't have any kind of ordering. So there is no base point here. We just take the three of them. That means that what we are going to define here, taking x1 as the first point or as the base point, or x2 or x3, doesn't matter. At the end, we are obtaining the same thing. But if we go back to Ricci curvature, we already had the same problem with Ricci curvature. That means that even for Ricci curvature, we didn't have this specific choice of the base point and what would be the second point in that case as well. So this number is somehow very well understood. This is for complete metric spaces, it wouldn't exceed from 2 from above, and for the minimum value, it would be 1. So for the minimum value, we have the condition. We already know what it is. So for the minimum value, what it means is that as soon as we constructed those initial balls, they intersect in triple. So it means that the triple intersection is non-empty. And then that means that there is a point that we said that if there is going to be an intersection, it should be on the boundary. So this point is on the boundary of the three balls. And that means that the distance from this point to each of the centers should be equal to the radius of that ball. That means that should be equal to the Gromov product. And this means that we have constructed a tripod with the center being the point that is on the intersection of these three balls. So although I draw this lines between these points, it doesn't mean that we already have the path, shortest path between these ones. And one more thing is that the intersection needs not to be unique. Then that means that we can have any number of tripods constructed corresponding to the number of the points that we get in the intersection. And another specific condition is when we take our 3 points from Euclidean plane or any cat-zero space. In Euclidean plane, this number rho is uniquely calculated, and the point that we obtain in the intersection of 3 balls after enlarging them with this number rho is in the convex hull of 3 points. So if we have considered this triangle constructed with these 3 points, then the intersection of 3 balls after enlargement would be a single point, and this single point is in the convex hull of these 3 points. That means that it is in the interior of this triangle. It is not just the case for R2. For any cat-zero space, this is the situation. That means that the intersection includes just one single point, and this single point should be in the convex hull of these 3 points. So now that we have this sectional curvature, we can compare different metric spaces to each other via this value, that how does the sectional curvature are related together. But as it is ordinary in the language of metric geometry, most of the time we do this comparison with Euclidean plane, because as we already see here, first of all, it is a really well-behaved function there. And then the other thing is that it doesn't matter which comparison triangle we take, we assume on the Euclidean plane. So comparing two metric spaces means that I already have my data set as X, and I have a well-known metric space like a sphere, like Euclidean space on the other hand. And I want to see how curved my metric space or my data set is. So I just want to compare it with the one that I already know. So either we take Euclidean space or any a special space like a sphere, tree, or whatever that is interesting for me. I can just take the same triangle on that space, like with the same edge length or with the same pairwise distances, and just compare this value in these two metric spaces. But the situation in Euclidean plane is that it doesn't matter which the comparison triangle we pick there, as is ordinary in metric geometry language. So I take one triangle from my metric space, construct the comparison triangle in Euclidean plane, and just compute two values here and just compare them together. If the value of this function on this metric space is smaller than the value on the Euclidean space, then I say my metric space is non-positively curved, otherwise it is non-negatively curved. So if the inequality is reversed, we say that it is non-negatively curved. So what does it mean in the perspective of intersection pattern of balls? If the function gives me a smaller value in the metric space, that means that I start with the same three balls in Euclidean plane and my metric space, but the balls in my metric space are intersecting faster than the ones in Euclidean space. So I get to the intersection faster in this space, in the spaces that have non-positive curvature. But the interesting thing is that how far we can go. So we already know that the least value that we can obtain is 1. And for people in graph theory field, it is like the R space is like a tree. So just listing some properties of this curvature and this curvature bounds is that it generalizes the concept of cat-zero spaces. Cat-zero spaces are non-positively curved space in the sense of Alexandrov. That means that we already have a restrictive assumption that our space is geodesic space. But the converse is not true. That is, we can have a even geodesic metric space that is non-positively curved in the sense of this example, in this definition, but it's not a cat-zero space like R2 and D1. R2 and D1 is neither non-positively curved nor non-negatively curved. And it is because in R2, you can find triangles that are as thin as possible. That means that we can find tripods, and on the other hand, we can find triangles that are as fat as possible. So it's neither non-positive or non-negatively curved. And the other thing is that always in these generalizations, one says that it is a generalization of the Riemannian version. So we have proved that this is the case for our definition. That means that if we restrict ourselves to complete Riemannian manifold, then non-positive curvature in this sense is equivalent to non-positive positive sectional curvature. And every tripod space, including metric trees, is non-positively curved. And the other thing is that when we go to Banach spaces, if this value, this function sectional curvature is equal to 1 and it is satisfied and obtains a minimum for every triple of points, then the space should be, if this value is 1, then it should be obtained a minimum. That means that the infimum should be exact and the space should be tripod. But even there is some more interesting situation for Banach spaces that if this condition satisfies and we also have intersection of 4 balls, then we should have intersection of any family of balls. So now I'm coming to the second part that I wanted to focus, to say that how this concept is telling us something about convexity of higher order. So the basic definition of convexity is existence of between points. That means that for any pair of points, we can find a third one that is between these 3 points, these 2 points. That means that the distance for each x1 and x2, there is a y. That's the distance from x1 to y plus distance from x2 to y is equal to distance between x1 and x2. And but from here we can go to hyperconvexity or totally convexity, hyperconvexity of order 2 or totally convexity. That is when we have the intersection of balls whenever the radius of these 2 balls adds up to be not less than the distance between centers. So if the radius of 2 balls satisfies in this condition, we get the intersection, and this is totally convexity condition. But then we can reformulate this condition into our version of the intersection. That means that the totally convexity means that whenever we take 2 balls around these points where the radius function satisfies in this equation, then we don't need to enlarge these balls to get the intersection. So the infimum value that we need to get the intersection for enlargement is 1, and it is exact. And if our metric space is complete, we don't need to check every radius function in this previous condition. So we don't need to take all the combinations and all the decompositions of distance between these 2 points. We only need to look for the midpoint. That means that we only need to take radius R1 and radii R1 and R2 to be equal on behalf of the distance between X1 and X2. And then from here, we go to 3-point convexity. What does it mean to have 3-point convexity? That means we whenever we take triple of points, there is at least one point that is between these 3 points. And with between these 3 points, we mean that it is between any pair of these, any pair in these 3 points. And again, if we want to formulate this one, we can just say that in the higher condition, it would be that whenever we take 3 balls, such that the radii satisfies in this condition, we get a non-empty intersection. And again, reformulating this 3 hyperconvexity, that means that whenever we take 3 points and a triple of radii for these 3 points, such that these radii are minimal subjected to this condition, then the infimum of the maximum, the sectional curvature with this radii and this point is equal to 1, and it is exact. That means that the infimum is attained by some point on metric space. So then what we did exactly was that we looked at this 3 hyperconvexity, but again, like in the case of 2 points where our metric space is complete, we took a specific radii. That means that in the set of minimizers on the radius function, we took a specific one, the one that satisfies the inequality for this condition. And this is not like that the 3 hyperconvexity is something that we introduced. It has been around for quite a long time, and we even have the infinite number hyperconvexity that is hyperconvexity. That means that whenever you have a family of any family of closed balls where the radii satisfies in satisfying this condition, then we have the non-empty intersection. So if our metric space satisfies in this condition, the metric space is called hyperconvex. Another reformulation of this definition based on analysis reformulation is that the metric space is hyperconvex or injective if every one Lipschitz map from a subspace of a metric space X to Y can be extended to a one Lipschitz map over all X. Maybe very first easy properties of these spaces is that first of all, every hyperconvex space is convex because we can just take the family of 2 balls and it satisfies in the totally convexity property, and it has the property. So know that it is convex. We can just replace the condition that we have here with binary intersection property. That means that whenever we take a family of closed balls that's a pairwise intersect, then we have the intersection of the whole family. And like another easy property that can one look from just the definition is that every hyperconvex space is a tripod space. I don't exactly brought here the definition of tripod space, but I brought the condition. It means that a space is called tripod if for any 3 points we can find a point that is between these ones. So the 3 hyperconvexity or the 3 convexity definition that I brought is exactly equivalent to tripod space definition. But the other ones that might not be easily observable from the definition, but are really strong properties include these ones. Hyperconvex spaces are complete and they are contractible to any of their points. These are really important properties and help us to find different statements on these spaces. And the other one is that hyperconvex space is an absolute one Lipschitz retract. That means that whenever we can isometrically embed it into some other metric space, then we have a one Lipschitz retract of that embedded or ambient space into this one. And the next one that is by itself very interesting is that just like the embedding of metric space into a space of probability measures, we also have the same situation here. That means that every metric space can be isometrically embedded in one hyperconvex space. And we can minimize this one. That means that we can find the smallest hyperconvex space that is called the event height span for this metric space. So as examples of hyperconvex space, the more well-known one is real line, complete R3s, and L infinity product of any family of hyperconvex spaces. So no, what I want to do is just saying that not just looking at hyperconvex spaces, I wanted to say that we can extend this three hyperconvexity to a family of balls. But the other thing is that this property that we can embed every metric space in isometrically into a hyperconvex space. This embedding is a very interesting one for us because this embedding is exactly what gives us these reduced functions of balls. So if in some sense we want to generalize this definition of sectional curvature to like a 4-point condition for hyperconvexity and so on, we need to choose the initial radius of balls, so the initial balls to start the scaling process and seeing when we are obtaining the intersection. So it is important to look at the space of reduced functions. So what would be the radius, the initial radii that we are choosing for this family of closed balls? And it is something that we exactly need to go to the hyperconvex envelope of our metric space to obtain it. So for this, we concentrate on finite metric spaces. For finite metric spaces, this hyperconvex envelope that is shown by A of x is exactly the set of functions on this finite metric space that satisfy in this condition. So it is very like analytic. Maybe it's not very well understood. Just to make the analysis a little bit more clear, we come to this set of functions where on this finite set satisfying in this condition. And then in this set of functions, we define this inequality that function f is smaller, not bigger than g, whenever for each x in our metric space f of x is smaller than or equal to g of x. And then we take the functions that are extremal with respect to this order that we defined here. And these functions are exactly the functions that satisfy in this condition. That means that these are the functions that are constructing the injective hull or hyperconvex envelope of our metric space. But maybe focusing on this condition, it is like exactly the situation that we want for our reduced function. So if we want to define a reduced function for our set of points that we picked from our metric space, and what we want is that we want to expect at least intersection. That means that we want the reduced function to be in a way that the radius around each point x and point y add up to be not less than the distance between x and y. So this is the simplest like first condition that we expect to have. And to making it minimal, that means that we want to go to the worst case scenario. So we have all the possible reduced functions satisfying on this condition, but we want to find the ones that are not very good. So the ones that if we make one of them smaller, make one ball smaller, we are missing one of the intersections in the binary intersection. And maybe giving another geometric picture of this hyperconvex envelope of the finite metric space, we can look at these functions. I call them reduced functions here because at the end they are going to be used as reduced functions. We look at all these reduced functions. Since x is finite, then that means that we are in some finite dimensional Euclidean space, and what we are defining here for these conditions is exactly for each pair we are taking the half space that is defined by this hyperplane. So we take this hyperplane and half a space above this hyperplane, we'll define one part of our space, and then we do it for any pair in our metric space, and at the end we take the intersection. So this intersection would be just the one delta x that we had in previous slide. And up to now, we haven't gone to the extremal points, extremal functions. We are just constructing this structure, which we see that is a polytop. But then we want to see that which part of this polytop is exactly the extremal function. What we do for that is that we take a function on this polytop, and for this function, we define a relation with respect to this one. And that means that 2 points are related according to this function if they satisfy in this equality. And for that, we can just take the support of this relation. That means that we take all the points that are not isolated in this relation, that there exists at least one other point that is connected to them. And then we define the smallest polytope that contains F to be the surface, to be the face that contains this function F and satisfies in this relation. That means that for including every function where the relation corresponding to this function contains the relation corresponding to F. So if it is like a little vague at the beginning, we can just look at this K of F as a graph on the vertex set and on the vertex set X, and we are connecting X to Y if F of X plus F of Y is equal to the distance between X and Y. And here we just have the inclusion of the graph. That means that we take all the functions that their graph, corresponding graphs include the corresponding graph of F. And the dimension of this face, it is a face on our polytop. The dimension of this face is exactly equal to the dimension of this WF. That means that all the vertex or all the points in Rx that satisfy in this equation. So why we are bringing this one? This is because, first of all, if X is finite, E of X is a polytop. These are the results. The finite metric space was mainly studied by Dures, and these are all the results that he obtained with his collaborators, different collaborators. So we have this lemma to connect the injective Hall of finite set to the structure that we introduced now. It is if we take a function in the injective Hall, we know that the face of corresponding face of that function is also in E of X and vice versa. And we know that S of F is compact, and we know that it is a spanning graph. That means that we don't have any isolated vertex. So these combinatorial equivalent conditions are really helpful to see that what would happen to the ball if we pick a specific reduced function. So we pick our specific reduced function in F. We can just look at the corresponding graph. the corresponding graph is defined according to this relation. That means that it somehow gives us the pairwise tangent balls, the balls that just meet on the boundary. So because the radius is not exceeding the distance, it is just exactly equal to the distance. So if we come here, we can just study all properties of this K of F, this is a spanning graph, and see what would happen if we pick this specific ball. And this is where I'm going to just look at the specific case that we had in our definition. That is, we took the Gromov product as the initial radius function, and the importance of Gromov product is that so what we have here is that we pick 3 points. We go to the injective Hall of these 3 points to pick a function as a radius function. But with this construction, we already know that the injective Hall of these 3 points is exactly a tripod. So if it is x1, x2, and x3, this point would be R1, R2, and R3. Exactly the Gromov product that we obtained. And as we see, if we look at this point is exactly a point between any pair that we have. And so there is one maybe property of this injective Hall that I didn't mention here, is that the value of this as a function from each of these points is exactly equal to the distance of this function f, call it f, distance from this to those points in the injective Hall. So that means that R1 is exactly the distance from this F to X1, R2 distance from F to X2, and R3 the distance from F to X3. And so what we see is that we exactly have as the corresponding graph, this graph, that if we can construct a graph for X1, X1 is F1 is on the geodesic connecting X1 to X2, is on the geodesic connecting X1 to X3, and geodesic connecting X3 to X2. This is structure. So that means that we have all the pairwise tangent balls around this point. So, but it gets a little bit tricky when we go from 3 points to 4 points to find the best function in the injective Hall to define the radius function. Because for 4 points, the injective Hall of 4 points is of this shape. And then for us, what is other than this worst case scenario, that means that we want to have the minimum radius function corresponding to the condition of pairwise intersection, is that we want to have the maximum number of tangent balls. That means that we want to have the maximum number of edges here in the corresponding graph. But finding such a thing here is difficult, because for any point that we take, any function, radius function that we pick here, we have the same situation. So we have the maximum number of edges in the corresponding graph. So, but anyway, this combinatorial structure helps us to define a kind of dimension. So if we want some combinatorial number or combinatorial dimension, it would be a good choice to just go to the convex hull of that finite metric space and just look at the space with largest dimension and take the dimension of that space as the combinatorial dimension of your metric space. For instance, for 3 points, the combinatorial dimension is equal to 1 because as we see the injective hull is just a tripod, so the maximum dimension of faces is 1. For 4 points, it is equal to 2. And again, for 5 points, it is equal to 2. The case that for 6 points has been studied by Storfels and Yo in 2007, I guess. And there is a package that you can compute the injective hull of any finite metric space. And I think at least for 7 and some couple of them above 7, I have seen the computation already. That's what happens. So maybe if I want to be on time, I will just go very fast through this summary of what we presented. So we wanted to find some geometric quantity with respect to intersection pattern of balls, the thing that we can relate to the scheme of TDA. That means that in our structure, if our metric space is really negatively curved, that means that implies that in the structure of check complexes, we have the check complex equivalent to Vietory strips complex up to triangle. And then there might be other generalization of these ones. One can just consider pairwise intersection as the initial condition, or one can go to higher order of intersection, like what would happen if in a family of n balls, any k number of them intersect, what would happen to the intersection of these k balls. And then it is the possible implication of this scheme to data set. What does this type of curvature tell us about the properties in our data set? So the theoretical parts of this presentation were included in these first 2 papers. We have already started applying this scheme to networks with our collaborator, Arijit Samel. And we have obtained some interesting ideas there, but we are like continuing computation on different networks to see that if there is something new in the network that can be captured by this scheme or this definition. So thank you for your attention. I will be happy to answer any questions.
Okay, thanks a lot for this great talk. Any questions or comments from the audience?